Well, it's official. Looks like we can get started. Welcome back, everyone. It's now week 4, so after the week is over, we're 25% done with the entire semester. Congratulations, we're getting there. For the announcements, I have pretty much just what you see on the page right here. But any questions right away? Oh, we got one through a chat. Okay, gotcha. Well, welcome back. I guess the announcements should probably start with the quiz, I'd say. That'd probably be the most important thing to talk about. One thing I mention about quizzes and remind ourselves quite a lot is that real exam questions are sometimes based heavily off these kinds of quizzes. Quiz 2 is due on Wednesday, the same day as the exam, but I don't have a late policy. If you got it into me Thursday or something like that, I would still take it for credit. But I encourage you to try to get Quiz 2 done as soon as possible, before Wednesday if it's possible. That way, every Quiz 2 that I get, I'm going to make a really strong effort to have them graded and returned back to you before Wednesday, the day of the exam. I'll be grading them primarily on Tuesday. So if you can make that effort to get Quiz 2 completed, that will help you do a couple things. You're studying for the exam now, and that will, well, you're also getting the quiz grade done as well. Any questions, folks, about the quiz at the moment or other questions? Okay. Other things I want to mention is our next exam is going to be Wednesday. That means Wednesday of this week, we won't have an actual class meeting. So that's always a little bit confusing for these fully online classes. I'll still hold office hours and things like that, but there's no class meeting since usually people are scheduling their exams for the actual time that we would have our ordinary class meeting. And plus, I'd say doing an exam and a lecture is just a little too much for one day. Also, because of this being an exam week, we're going to think of our exam as the quiz assignment. So there's not going to be another quiz as well. That's, again, just too much stuff going on at one time. So I guess for what we're at so far, we're going to finish off the section 2.4 notes. There's a couple of practice problems that'll help support what we're doing in section 2.4. Then, like we mentioned, I'm going to turn over everything to the class, and we'll take whatever questions folks might have about the upcoming exam 1. They could be from these documents down here, questions out of the homework, anything like that. I'd be happy to help out. If we run out of questions, the extra section 2.5 is down here as well, and we can start looking into those notes. We probably won't go too far into those notes if we're running short on time, but that's just there just in case. Well, any questions whatsoever, folks, before we get started? Okay, let me clear off these announcements. And here's where we left off last Wednesday. Last Wednesday. Just as a refresher, this is the first one on example 5. We got 2 of these done, but let's spend some time on this one just to take a look again how everything went down on this one. This limit is special because we're heading towards a finite number, -3. We're not going to neither positive infinity nor negative infinity on this problem. And so when you see a finite number there, our first thought is try to use direct substitution. We tried to plug -3 into the denominator, but that actually gave us a 0. That would have been +9 plus 3, so it's 12, minus 12 for a value of 0 altogether. So if direct substitution fails, next thing we do is we change the function algebraically. The technique we needed was just factoring. That allowed this cancellation, and now we have x divided by x minus 4. This is a nice rational function. Once we get to this stage, we observe that -3 for x can be input to that position. It does not cause a division by 0, so now we have the value of the total limit being 3/7. Any questions, folks, about the refresher there on that part A? Okay, then there's this remark that we've had on the notes several times. It says for full credit on quizzes and exams, correct limit notation must be used. Let's take some time to just say exactly what we mean by correct limit notation. What we mean by that is, let's use this pen right here. We cannot say x divided by x minus 4 equals -3 minus 4, because this equality here is just totally not true. On the left, x divided by x minus 4, its value depends on x itself. It gives us a whole curve in the xy plane, whereas this is just a constant. So correct limit notation means we have to say what we mean and mean what we say. We meant as the limit as x approaches -3 of that function, we get that result. So let's add here the comment. We must use correct limit notation and write limit as x approaches -3, x divided by x minus 4 equals the -3, -3 minus 4. Then we would simplify the thing on the right. So the whole statement here on the remark is just a reminder that this is a bold-faced lie. I mean, we kind of know what you mean, but to be exactly explicit about what you're trying to say, the limit statement is required at that spot. Once we take care of the limit by direct substitution, notice we stop writing it. So it's not here nor here in the answer. Well, let's imagine that the exam had a bunch of limits and you didn't write this down on every single one of them. It's not like you're going to fail that exam. You might lose a point one time. I might write, you need correct limit notation, but you're not going to be double dinged on that. There's no double jeopardy. Well, any questions, folks, about that discussion on the correct limit notation? Okay, well, let's go forward through the problems next. So in part A, we just had to factor it and that we could use direct substitution at that step, highlighted in yellow. I think this one is a little bit trickier because it required an ordinary conjugate. So if you see square roots in the problem and you can't put a 0 in for h, like you see there in the denominator, this is the method that you have to use, a conjugate. Now we're going off to new territory. This one actually looks worse than the prior one, but it's not so bad. So this will be our first problem of the day. The first thing we take a look at when you see a problem like this is you always want to wonder, ask yourself the question, could you plug in 0? Well, up here, if you did that, you would get 25 minus 25. It's okay to have 0 in the numerator, but that's the problem right there. You cannot plug a 0 in for that h. So the whole goal is on this one, algebraically, cancel h in the denominator. When I see I missed a chat, sorry about that. Let me take a look. Alif says, maybe a silly question, but do you want limit notation in front of the final answer? It wouldn't have to be in front of the final answer. If, for example, you're meaning, say, like over here, you wouldn't want the limit statement there. But you could write a final answer that kind of goes like this. That whole quantity there equals 3/7. If you're thinking in those terms, then yeah, that would be an appropriate way to write it out. Does that answer your question about that, Alif? Awesome. Glad to hear that. And I don't think that's a silly question at all, in all honesty. Anything with relation to limits, the first time you see it, it's all weird at first. It comes together a lot more in chapter 3 once we show what the purpose is of these limits in defining the derivative. But for the moment, it's all just kind of new stuff. So we get just getting used to what are the things to write, the things to say, and the things to watch out for. So our whole goal on this one is that h right there is the biggest problem. If it was gone, you could substitute in 0. So the moment that's canceled, we're in business. But we can't cancel in cross addition and subtraction. We can't cancel into this group with the power 2. What we need to do is just expand that -5 plus h squared. So here's the big technique on this one. -5 plus h squared. If you're a little rusty on algebra, no worries. This one has to be completely FOILed. So the review on this is you'd want to write it like this to visualize it. -5 plus h times -5 plus h. Then in that form, you can FOIL it out. The way I visualize it is I take where the red dot is and just distribute it into the group on the right. So first it's -5 times -5 for 25, then -5 times h. Then move over. This h is going to distribute into the group on the right in the same way. We'll get negative 5 times h, so negative 5h, plus h squared. So this is altogether 25 minus 10h plus h squared. And that's going to take the role of that part right there. So we're on our way, folks. This limit hopefully is going to work itself out after expanding that. So my first step is really just to substitute in what we just did. It's now the limit. H is getting smaller and smaller, going to 0. And negative 5 plus h squared became 25 minus 10h plus h squared. Then minus 25, that was already there, and divide by h. So that's our first step on that one. Once you take that step, you'll notice, well, there is a cancellation. We can cancel this 25 with this one. So now more writing. This is now equal to limit h goes to 0, negative 10 h plus h squared, all of which is divided by h. So let's recap of where we're at on this one. At the very start, by the red dot, you cannot cancel that h into the numerator. That subtraction here by negative 25 is already enough to prevent us. Here, we still can't cancel because we can't cancel across negative in addition. But over here, you can cancel. There's two ways you might view it. If you're comfortable canceling this h and this h, dropping it to a power 1 right as it stands, I'd say go for it. But if you feel like you're a little bit rusty on algebra, you want to be very careful, this is the careful step the author usually would take next. Here, we're back to factoring, so we'll factor out the greatest common factor, which is just h, since h divides both of those terms. So factoring that out will give us limit h goes to 0. Here's the h factored out. It divides into these terms once you factor it out, so this will just be a negative 10 plus h squared divided by h. We'll drop the power to just h power 1, so h, all of which is still over h. And now we've met our big goal with this problem. The h in the denominator can cancel with that h up here outside the factor. It leaves behind negative 10 plus h, so now we're just about ready to satisfy the limit or fully solve it. Next step is limit h goes to 0, negative 10 plus h. This new function we have here has no denominator whatsoever. And so when we say h goes to 0, that's happening here where it's highlighted in yellow. That's now just a glorified number 0. That means we're about to write out our end answer. This is negative 10 plus 0. And notice we didn't need the limit statement right here. Once the limit's evaluated in this way, by plugging in the number, we're all set. The whole value of all of this is negative 10. So this is saying as h gets closer and closer to 0 from either side, that rational function in the variable h approaches negative 10. You can get close to as negative 10 as you'd like. Well, any questions at all, folks, with that first problem of the day?
I have a question about when you don't factor out the h, but if you were just to simplify it yourself.
Oh, yeah, absolutely.
So do you cancel out the h that's with the negative 10 and one of the h squared?
Yes, absolutely. So you just have to make sure everything, numerator and denominator, gets divided by h, and then that would work algebraically just fine.
Okay, thank you.
Yep, absolutely. A lot of people do that in their personal work. Me too, if I'm just doing some math and I'm not putting it on the notes, I usually do take that step. I would have canceled, just to visualize it, here, here, and I would have done this, just canceling off the power to remind me that h is left over. So you'd be expecting negative 10 plus h. Other questions at the moment? Okay, I have a couple more on here, but so far I'd say A, B, and C, those are the major ones that you would see on a real exam scenario. Because the algebra doesn't get too out of control, the biggest trick is knowing that a conjugate can appear when you're dealing with the square root, or knowing that you need factoring. This denominator is factored by trial and error. So I'd say A, B, and C, pretty routine problems that you could expect on a real exam. Parts D and E are just more practice. It's going to help with the homework too. There's a couple, I think one problem, maybe one or two problems in the homework where it looks about like this, just a little bit more out of control algebraically. Any questions at all, folks, before we start these last two?
Could you go over B again?
Yeah, absolutely. So on B, oh yeah, this one with the conjugates. So the trick with this one, let's just pull it out of here because it's just too much going on. I'm going to drop it over here. So yeah, here's the one with the conjugate. And let's just call this a second look at part B. And they'll hit part D right after. I'm glad you mentioned that because in my opinion, out of parts A, B, and C, I think that one's the worst because if I saw this in an exam situation and I just didn't think the conjugate, there's no way I'm going to make progress on this one. It can be kind of frustrating. Doug asks, does a late policy apply to our homework? No, it does not. As far as the homework goes, you can always request an extension. So on your homework list, there's going to be a location that says the past due assignments. Let me actually just pull that up just to show how it goes. We'll come back to right here. Let's see, I need a browser. That won't do. Let's go here. That doesn't look comforting. Let me try again. Okay, that looks a little bit more legit. My password was found in a data breach is what that said. That's exciting. Let's keep on going. Okay, so imagine you just logged into WebAssign. They may or may not have told you your password is in a data breach like mine. But where you want to look is right on this tab right here where it says past assignments. If you click on that there, then there's another button where you can go and click on request an extension. Then you just put in the time and the date. You don't have to put anything here on this box. I don't need to delve into your personal life. You don't need to let me know unless you feel like it's pertinent with school. So it's totally fine to just leave this blank. Put in a time that seems reasonable. There's nothing wrong with putting it a week out, something like that, and click submit. What then happens is it fires an email to me, and then I just go into the system and approve the extension. You can request an extension as many times as you like. It'll never annoy me. Does that make sense about how all that works? Awesome. So yeah, there's no late policy really on this except the request the extension button. But once you go and rework those problems, you get full credit for that. Okay, now we're taking another look at this nasty problem right here. So limit as h goes to 0, root 1 plus h minus 1 divided by h. And the idea here is we need to multiply it by the conjugate of the numerator. So let's just write something out. The conjugate of root 1 plus h minus 1 is root 1 plus h plus 1. So we conjugate by just changing the signs in the middle. And you can imagine there's two ways to say this. We can also say, and the conjugate of root 1 plus h. Let's say it was a plus 1 here. Then we would say its conjugate is root 1 plus h minus 1. So the idea of finding a conjugate is looking at the form of the fraction, changing the sign in the middle, and then you're all set. So here's where it gets a little dicey. The problem starts out in a nice simplified form, but we're making it more complicated on purpose. This turns into limit h goes to 0, root 1 plus h minus 1 divided by h. And I should also expand a little bit on why are we making it more complicated? Well, it's because the limit is going to 0 right here. And if that's the case, you'd be dividing by 0 in this denominator if we were to use direct substitution right now as it stands. So our goal is cancel that h in the denominator, just like on the prior problems, so that direct substitution will work. So coming back over here, observing the sign in the middle. Oh, I lost a annotate tool. Give me one moment. There it is. Okay, observing the sign in the middle here by the red dot, we're going to multiply by the glorified number 1 in the form root 1 plus h plus 1 divided by root 1 plus h plus 1. We're going to have to FOIL out the numerator, but we'll just multiply h next to this group in the denominator. So here's the next step, multiplying everything through. Any questions at all where the red dot is? Okay, this one gets a little bit dicey. So here's how it would look if we wrote it all out carefully. Its limit as h goes to 0. We'll have one big bar here. Let's do the denominator first, since it's the easier one. It's best to leave h factored out. So I'm going to write it as h multiplying root 1 plus h plus 1. Our goal is to cancel that h. If we distribute it into this group, it's just making the work of canceling harder. So this is the best format to leave it in. Plus, it's more writing, so no reason to do that. Up in the numerator, we do have to be careful. So first we multiply here to here. A root times the root with the same thing inside just gives you the thing inside, the radicand. So this becomes 1 plus h, the square root cancels. Multiplying here to here, that's 1 times 1 plus h, so we get plus root 1 plus h. Now let's go, how about green this time? Carrying out the FOILing, let me put parentheses around here just to indicate we're FOILing out those two groups there and there. We take the negative 1 multiplying this group. That's negative root 1 plus h. And lastly, negative 1 following the colored arrows will be negative 1 times positive 1, so minus 1. And that means we have a cancellation here and here. That's the beauty of the conjugate, is that it always causes a cancellation in the middle, only because we swapped the signs. We just engineered that to happen. And with that canceled, notice also there's more cancellations. Positive 1 with negative 1. That leaves just the h in the numerator, which we can cancel with h down below there. But let me write one more step, since that's a lot of cancellations just for this line. Cleaning this up a bit, it now looks like this. We're taking the limit as h becomes smaller and smaller of h in the numerator divided by h times root 1 plus h plus 1. Any questions at all so far, folks, to this stage? Okay, we did all of this crazy work with the conjugate because of those cancellations there, and now it gives us a cancellation right here. This h can cancel cleanly with this h. It leaves a 1 in the numerator, so I'll just write it in just as a reminder, that 1. So now we still have to write limit as h goes to 0. But all we have left is 1 over root 1 plus h plus 1. So it's always good to remind ourselves, why did we do this algebra? Is because of that h right there in the denominator on their very first problem. But once we canceled it, direct substitution works right here. You can plug a 0 into that location. You just get square root 1 plus 0. That turns into the square root of 1. So now it is 1 over square root of 1 plus 1. Because we did direct substitution at this step, we dropped the limit statement. Now we're just working with ordinary numbers. Square root of a 1 is a 1. So we just have 1 plus 1 in the denominator. And we could call the whole thing 1/2. So what this work is telling us is that as h gets closer to 0 without bound, this whole function here with the h's highlighted in gray we'll get closer and closer to a value of 1/2. Well, any questions at all, folks, with that second look at part B? Okay. Well, again, A, B, and C, I'd say, are kind of the more routine problems, but these are still pretty important to take a look at. The algebra is a little bit rougher. That's why they don't make good exam questions. I'm not going to try to write a really long question on a timed exam, but they are problems that you'll see some of in the homework. So we ought to do these just to help out with the homework. And we still do get some good exam practice looking at how these go. So part D, let's see if we have enough space to do that. Let's put it maybe on the new page. So part D has the same kind of problems as before. If you try to take 0 and directly substitute it in here or in those two positions, we're dividing by 0 twice now in both fractions. So there's nothing we can deal with a conjugate. There's no immediate factoring that's going to help us, although we'll see factoring does a little bit. But the idea with this one is if you have two fractions, then let's put down this color here. We must add the fractions. But if we have to add the fractions, that means the next thing we want is we need a least common denominator. But in order to get a least common denominator, you need to factor both of your denominators fully. Otherwise, finding the least common denominator does become tricky. On the first fraction, 1/t, t is considered fully factored. You can't do anything with that one. But you can factor those. So let's say here, for the next thing we need to do, we must factor all denominators. Let's say, if possible. The if possible is just to remind us I can't factor that t as it stands there in a reasonable way. So here's step one. This becomes, let's actually give ourselves a little bit more space. I'll drop it down here. It's now the limit as t goes to 0 of, make this a longer fraction bar because we're going to add some stuff. It'd be 1/t minus 1/. Now to factor that denominator, anyone see what the technique should be for factoring t squared plus t? What would you do on that one? Exactly. We're going to have a t plus 1 by just factoring out the greatest common factor t. So good call on that one. So if you notice that there's a factor of t here because it's t times t for t squared, another factor of t, then you can just pull out that greatest common factor. So here's t, divide it out, and you have t plus 1 left over. Now, to get the least common denominator, once the denominators are factored, we can now say, let's use a different color here. The least common denominator is equal to this one, t times t plus 1. And the process of getting a least common denominator just now amounts to make both of these denominators completely identical without changing the equality right here. And we can make that happen. If we look at the smaller denominator, it has the factor of t, so we do not include that one. It's missing t plus 1, so we just multiply it in. Here's t plus 1, t plus 1. Much like with the conjugate trick, this is just a glorified number 1 because they cancel. So we're not changing equality at all in this one. But what we did get is the least common denominator. Now we can actually subtract across the numerator as we see it. Any questions at all, folks, on getting that denominator all set up? Okay, we're going pretty slow on these because it's really just a huge review of algebra, really, until we get to the point where we can substitute 0 into those values in the denominator. So on our next step, this is what it will look like. It's a limit as t goes to 0 of one big fraction bar, where we're going to put the greatest common denominator down below, t times t plus 1. We only write that in once. Then we go across the numerators. Here we had a t plus 1. Times 1 just gives us the t plus 1. And then from here, go minus 1. So we had something awful to start off, but after correcting this by adding the fractions, this is starting to clean up. We have a cancellation already. The positive 1 and the negative 1 will cancel off. That means we can also cancel the t, but that's kind of hard to read the notes. Let me take one more step just to clean it up a bit. It's now limit as t goes to 0 of t divided by t times t plus 1. So here's our cancellation. That t and that t cancels. I like to put this 1 here because I need to remind myself a 1 is going to carry into the next step. So this turns into limit t goes to 0 of 1 over t plus 1. Now we couldn't do direct substitution at the start of the problem. In the middle steps, we couldn't do it here, here, nor here. It's right here by the red dot where suddenly direct substitution is on the table. You can allow t go to 0 right there, and this does not cause a division by 0. So we just about have an answer. It's equal to 1 over 0 plus 1. That's just 1 divided by 1, which is finally equal to 1. Definitely kind of an adventure on this one. But how do folks feel about it? Did it make sense on adding the fractions and the rest of the algebra? Okay, so if you see something that just looks like it's a bit nastier in the homework, come back to these notes to get some motivation on how to start it. But as always, don't hesitate to hit the Ask My Instructor button. I'll be happy to help out that way as well. Well, let's keep on going. We have one more problem for the notes, and then we are done with section 2.4. Just in case, I think we might be able to fit this one in here. We don't need to make this turn into pages and pages. So here's our last one for the notes. This one has, well, it looks pretty built up. Feels like there is a lot going on in this one. The type of fraction we're dealing with this time has an interesting name. This is called a complex fraction. What makes it a complex fraction is it's an ordinary fraction to start, but in the numerator of my fraction, I have a fraction. Anytime something like that happens, we call just the whole thing a complex fraction. So to find the limit of this thing, notice we have the same kind of problem as before. X is going to 0, but you cannot directly substitute 0 right here because that's a division by 0. So we have to do something algebraically to clean this up in order to do the direct substitution. Well, this one's kind of similar to the prior part. In order to simplify a complex fraction, we need to first find the least common denominator, which means, just like in the prior problem, we look to our denominators. By our denominators, we mean this one and this one for each fraction in the numerator and the denominator. The denominator has a denominator x. You could think of it as a fraction, but it has a denominator of 1, so less interesting. The interesting denominators are these two, x minus 1, x plus 1. Let me use a different color for that. So we can now say the least common denominator equals x minus 1 times x plus 1. So we're going to multiply the whole fraction by that thing in the numerator and in the denominator. Any questions at all, folks, before we start their first official step? Okay, well, let's get this started. On step one, oh, give me 1 second. I think I have a weird issue on this. I think my computer is just getting slow. Okay, I think we're about ready. So on the first step, let's call this limit as x goes to 0 of 1 over x minus 1 plus 1 over x plus 1 divide by x. And we're taking that whole thing, multiplying by the least common denominator, x minus 1, x plus 1. But you can't just multiply by something like this without damaging equality. We've changed the function. So what we do next is we divide by the same quantity, x minus 1, x plus 1. And now we're just multiplying by a glorified number 1, really, after simplification. Dana asks, why is the least common denominator already combined? Well, what made it come out just like this way was due to the fact that these factors, or excuse me, these denominators are already in a factored form. They're distinct. So we just combine them in this way. In other words, if we had x minus 3, x plus 4, and if this one was down below something like x minus 7, we would take all the denominators we see and just combine them in this way. Does that make sense about the least common denominator, Dana? Okay. Another way to think about it is just in the view of the last problem. Let me just make sure I get those out of there so the notes doesn't have that additional thing put in. But another way to think about it is this one had the least common denominator where you could have taken a t times t squared plus t, but that would have given you just a common denominator. It would have been a higher power than you really needed. So on this one, we had to take this t and the t plus 1 from right here and put those together. Notice we only took, or let me see if I can highlight this a little bit better to address that question. Here we had a t, let's say before we actually put in that correction. On this one here, the t squared plus t, we factored it to that location. So now we have a t times t plus 1. So we pulled this is where we were looking, when we brought it over to the least common denominator. But notice we only took t one time. We were just looking for a fraction, or excuse me, an expression like this one, so that when we plug it into the numerator here and here, the denominators are going to fully cancel out. Well, on this one, you could have just said it was one side as well, because notice we essentially just took that right there and made it our least common denominator. But if this one right here was something else, say maybe it was a t plus 6, we would have had to put a t plus 6 here to adjust. Does that make sense about the pulling from one side versus both? Oh, the reason it's not t squared, that's a really good question. Let me see if I can back off the highlighting here. Got to love Control Z. So it was here to start. And the issue about the t squared is if you went, let me use a different color. Let's go with purple, should be a good one. So let's just ignore that for the moment and say you went common denominator equals t squared times t plus 1. This would actually work. You would have to put here times t over t. So this would be t power 2 times t. Over here, you'd have to put t power 2. So there have to be a times t here, and that would actually work. So the reason we used just t times t plus 1 is only because it had a smaller power, making it the actual least common denominator. So bringing it back to where it originally was, see how much Control Z remembers. The reason t times t plus 1 works is that's the smallest thing you need to have in order to make both of your denominators completely equal. So if it looks just like this, in order to get your denominators equal, that's all you would really need, because all that's missing from right here is that t plus 1. So we put in a t plus 1 here, and observe our denominators are completely equal at that step, meaning we have the least common denominator here. These are really good questions. Honestly, least common denominator can get really tricky as a concept. Does that help so far in exploring what was going on with this one? Yeah, absolutely. I'd say probably the best way to think of least common denominator in a part D question like this one is you're just trying to get your denominators to look exactly the same. But I see the confusion as well, thinking about this one a little bit more with you. What makes part E trickier now when we take a look at this one is on this problem, we're not actually even trying to add those two fractions together. We're just looking for an expression, we're calling it LCD, such that if you take this and put it into every single numerator, we want the denominators to cancel out. So our view of the least common denominator is different this time. In this problem, let's actually add that to the notes just as a clarifying. In this problem, because it's a complex fraction, we are using the least common denominator to cancel x minus 1 and x plus 1. So our whole problem on this one is the fact that it's built up right here. It became a complex fraction. So if we can eliminate x minus 1, x plus 1, then we cut the fraction down to size and makes it manageable. So what we did was we looked at all the denominators. There's just two here. When we mean that, we mean among the numerator and the denominator of the total fraction. In this fraction here, we went x minus 1. From this one, we went x plus 1. Now in this arrangement, we're going to take this x minus 1, x plus 1, and it has to distribute here and here. So let's write that out. It'd be limit. Oh, didn't mean to do that. Let me fix that. There we go. It'll be limit as x goes to 0 of, first, this portion right here is going to multiply to that location. So it's going to turn into x minus 1 times x plus 1 divided by x minus 1. Next, this numerator is going to multiply into this location. What we're doing here is using a property of fractions that to multiply fractions, you just multiply the numerators across and the denominators across. So this next one becomes plus x minus 1 times x plus 1 divided by the x plus 1. And last, we need to take this and multiply into the x. But just like in the last problems, it's best to leave x factored out. I would just write it this way: x times x minus 1 times x plus 1. So backing off to this step, the strategy was, once you find the least common denominator, x minus 1, x plus 1, we essentially just multiply it into every single numerator in the fraction. So it multiplied here, where it's highlighted in yellow, here, and here. Why would we do all that? Well, again, it's to try to get a cancellation. Over here is one cancellation. X minus 1 cancels with the x minus 1. New cancellation over here, x plus 1 with x plus 1. And this is the smallest expression in terms of degree that will allow that cancellation to go through. The next step is just cleaning it up. It's now equal to a limit as x goes to 0 of x plus 1. That came from over here, then plus x minus 1 that we see on the right of the red dot, all over x times x minus 1 times x plus 1. So it's getting there. But again, these are some pretty long problems. This is like the worst one of the whole set. Doesn't make a great exam problem, but stuff like this is in the homework. The whole reason we did all this algebra is because x is tending towards 0, which causes a division from 0 right here. So if you can eliminate that x, the whole problem will just completely be satisfied. That x highlighted there or circled there is in that location, and in now that location. So now if we can cancel that x, we can do the limit really, really fast. But notice we're pretty close to making that happen. Plus 1 and minus 1 cancels. The x's that we see in the numerator, they combine. So we now have, it's equal to the limit as x goes to 0 of 2x up in the numerator, divide by x times x minus 1 times x plus 1. That's kind of exciting because now we can do the cancellations we would like. That x cancels with that x, leaving just a 2 in the numerator. So once that x right here was eliminated, here's the direct substitution step. As x goes to 0, that quantity goes to 0, and that quantity goes to 0. So the whole thing turns into 2, 0 minus 1, 0 plus 1. The denominator is a glorified -1 times +1, so this is just 2 divided by -1, giving us a total value of -2 in the limit for this one. So this one looks like it was a lot of steps, but really, you could have went from here and just went immediately to that step there. The step in the middle that I showed was just to show algebraically what's actually even going on when you clear denominators in that way. Well, that's one approach. If people prefer to just add the fractions, that honestly works just as well. This is usually the faster way that the author would show in this kind of context. Cameron says, I'm confused why we didn't bring the brackets down in the numerator. Oh, you mean these parentheses here? I think the reason I dropped those, Cameron, was once I distributed from here to, from here to here, sorry, go ahead.
I actually mean the next step. So we get like x plus 1 plus, so.
Down here?
Yeah.
Gotcha.
Because I thought that would imply we'd end up with basically 1 over x.
Let me see where you're looking.
And cancel out from the brackets, if that makes sense.
What do you mean by the brackets? Do you mean these ones right here, like that x minus 1?
Right.
Oh, gotcha. The trouble with that x minus 1 right there is, let me get the eraser going. Because of that plus right here, we can't cancel this x minus 1 across the addition. It would have had to look more like this. If it looks like this in a fully factored setup, then you could do all those cancellations and it would turn into a 1 over x, like you said.
But if they're being added to each other, when we get to that point, we can just delete them? Because they were... Oh, I guess they weren't before. Okay. I think I'm tracking.
Gotcha. Yeah, this one's just nasty, honestly. There's a lot of algebra. Just look how high the stack of one step is. That's pretty abnormal for math. But other questions at the moment? Okay, again, to me, this is kind of a worst case problem. It's meant to help out in the homework more than anything, but I don't think it even gets at as bad as this one in the homework. This one, part D, would be a little bit more routine for a nastier homework style question. But this one was really more about extra practice, I'd say. Well, congratulations, folks. That means at this stage of the notes, we have completed off section 2.4. Any last questions at all in section 2.4 before we turn it over to exam review questions? Okay, let me close this file just temporarily. Oh, I didn't close the file I wanted. That was Moodle, I think, or something. No, Moodle's here. I closed something. I don't even know what it was, but I'm sure that's okay. Where is my X button? There it is. So we did it, folks. We're done with section 2.4. With where we're at in the class, we have about 24 minutes. I don't think going into continuity is going to be a good idea. So I'm going to take this section we see right here and just move it over to the next week. So we're now at the part of the class where we're calling this an informal student review. I'll turn it over to you all next. What kind of questions would you all like to take a look at next for the purpose of exam review?
Is there a link where we can schedule a time for our exam?
Let's take a look. So, oh, for scheduling the exam, sorry. Yeah, what happened with that was I sent everyone in the class an email with instructions on how to schedule theirs. Let me pull a quick pen out. But what was your name? I could take another quick look at that and resend the email if necessary, or if I missed it entirely.
Eli Hyde. I can also check right quick. I don't know if it got sent through or not.
Gotcha. I'll double check. And the reason that's kind of a tricky question too is it all depends on the testing center. If you're testing in the Pocatello Testing Center, then I have a phone number that I need to give to you to call them up and schedule a time to take your exam. And if it's the Idaho Falls Testing Center, then I need to send you a link that gives you a way to schedule appointment with the Idaho Falls Testing Center. So it's a little bit confusing depending on which testing center you're closest to. So let's see here. What else was I going to say? Oh, yeah, I did have one other thing to say. The exam is held on Wednesday, September 11th. That's just the official date for the actual exam. But the reality of scheduling an exam for an online class like this one is testing centers do fill up, whether in Pocatello or Idaho Falls. So you can, in fact, schedule your exam from any time between, I mean, you could schedule it now, but I think most people are not wanting to schedule it earlier, unless it just works out in your schedule better. 11th is the official date, but you could also schedule it for the 12th and even as late as the 13th, and that would still be considered doing your exam on time. Any questions about that or otherwise? Okay, so if you haven't done so yet, check out your ISU email. I sent out instructions on which testing center to contact. If I gave you the wrong testing center, if you decided, hey, I'm closer to Idaho Falls, I don't know why I was given the Pocatello testing center, just send me an email right away and I'll give you the right information. Emily asks, about how many questions long is the exam? Is it a lot longer than the practice exam? I'd say my exam is actually pretty short. And I think I asked, oh geez, that's a good question. I'm kind of foggy how many questions I asked, but I think it's between 6 or 7 questions. And by that, I mean, if we take a look at, say, this sample exam, I think I asked a question that looks like these kinds of things where there's graphs. Other questions where might look about like, say, this kind of question with multiple graphs at once. And I asked a couple questions along the lines of just doing the kind of limit computations that we've been doing, whether it's something like problem number 10, where the limit is heading towards a finite number, or if it's something like problem number, let's go up here. Problem number 3 in section 2.2. These were special limits as we were heading towards positive infinity or negative infinity. And so as far as the similarity and difficulty, I'd say that they're very in line with what we were doing. So as far as studying for the course, this sample exam problems version 1, some of these get a little bit more challenging because they're more for the sake of practice. The one from version 2, these are the textbook problems that we've been looking at. But the actual questions that I'm going to be assigning are going to be very similar to the ones that you've been doing on the web assigned homework. The ones on the quizzes, again, kind of a hint is that That's going to be a pretty similar question that you'll see on the real exam. So the sooner you solve that one and send it in, the quicker you'll get feedback on how that one should go. And my questions are going to be highly similar to what you've seen in the notes. Say, for example, in the section 2.4 we just completed, I'm looking for questions that go a little bit more along these lines, like we mentioned, parts A, B, and C, because they're more directed questions. But I'm not going to go for like the one we just solved here, where that's kind of a long algebraic slog. I'm looking for just the major thrust, the main ideas on the exam. So it'll be similar in difficulty, but they'll be on average a little bit shorter questions than the ones that we saw on the actual lecture notes. So I believe I wrote an exam that's about 6 to 7 questions, similar difficulty to what's in the notes, but they're also shorter questions because it has to go along with this being a timed exam as well. Other questions about the exam or study questions folks would like to take a look at?
On sample exam number 1, can you review number 7?
Absolutely. Looks like Dana beat you just under the wire there on question 10. So let's take a look at, oh, it's going to be 75 minutes, the same as a class meeting. So I heard from, in the text, we're going to do problem number 10. And I'm so sorry, over the voice, what question were you asking?
Number 7.
Number 7, okay. I'll just put these over here on the margin where you see on the left, and we'll hit them as they come in, over voice or over chat. So number 10 first. Let's take a look at that. Anyone in particular you want to give a try? Looks like there's some pretty good ones in this set. Last two. Yeah, let's take a look at these two. And as far as where these are going to go, we're solving these as class solutions. I'm going to put them probably right here. I'll just call it class solutions when I upload them. I should give this a name so I don't forget to do that. How about a better name might be Exam 1 Review, since that's what we're doing. Okay, so here is those two. They don't look like the friendliest things ever, but let's give them a try. Starting with this one right here, limit as t goes to 0, root 1 plus t minus root 1 minus t over t. Well, this one involves square roots, so that's a good indication that looks like we need to use the conjugate. The trick is, if there's a negative sign right there, we convert that to a positive sign. And then everything else in this numerator is identical. So root 1 plus t, root 1 plus t, above and below. Let me try to put that number 1 in better. 1 plus t, then root 1 plus t. Okay, so that's the major idea to get started on this problem. And if this was like a 6-point question on the real exam 1, I would give 2 points partial credit just for writing that down, because you're indicating to me that you know how that problem starts. It needs a conjugate. Now we have to get through the details of it. Parentheses are optional, but it just reminds me I'm foiling it out on the next step. Dana says, so you change both the inside negative to a plus and the middle one. Oh, that was a mistake on my part. Thanks for spotting that, Dana. If I was forming a conjugate, I should have only changed the highlighted yellow signs. So let me put this correction in. It's a correction, so I think that redder color does the job. That should have been a minus and a minus. So the plus had to line up to here, and the minus had to line up to there. Thanks for catching that. Okay, on the next step, we're just foiling this all out. So now it's limit t goes to 0. And there is a big cancellation on this. A lot of times when you're writing out these problems, you're not going to write down the middle two terms because they're always going to cancel. But I'll do them here on these notes just to show how that goes. So first we multiply here to here. It's a root times a root, so it leaves a thing inside. 1 plus t. Multiply here to here. This is going to be, well, it looks awful. It's plus root 1 plus t times root 1 minus t. I decided not to do anything much with it since our goal is to try to get that to cancel. Now, next multiplications, different color arrow just to highlight the next step. We're multiplying those two roots together. The leading sign is negative, so it's going to be negative root 1 minus t times root 1 plus t. And the last multiplication is here to here. Never make these fraction bars long enough, it seems like. Let's go a little bit longer. It's multiplying with the leading term negative, so we do need to put a negative here. Our root 1 minus t times the same root 1 minus t leaves 1 minus t, but this time it does need parentheses. The 1 minus t has to be multiplied by this leading negative sign. I think the parentheses right there would be the hardest thing about this whole question. If this was a real exam question, I probably would simplify the function a little bit up here just to make it more manageable for a timed exam. Well, that handles the numerator. Next, for the denominator, we're taking t, multiplying that group without actually distributing it. So it's t times root 1 plus t plus root 1 minus t. And there it is. After multiplying by the conjugate, this is the result. Any questions or comments, folks, to that stage? Okay, so next we have a cancellation here. Root 1 plus t times root 1 minus t. Subtract the same quantity, means those terms are gone. I'm going to take an extra step to do that distribution with a negative sign. So let's call this all together. It's a limit as t goes to 0. 1 plus t to start. We distribute this negative sign into the group, just flipping the signs to get negative 1 plus t. Don't like my negative 1, let me fix that. Then down below, it's t times root 1 plus t plus root 1 minus t. So next set of cancellations are the positive 1 and the negative 1. Now it's equal to limit t goes to 0. In this numerator, it's just a 2t now. And the denominator is now t times root 1 plus t plus root 1 minus t. This one is just about done, but really the challenge I think with this one is there's just a lot of stuff to write down. I mean, I already made a mistake right here where I should have copied a negative sign coming from over here. So I think probably the good skill in this is go carefully, try to organize it as best you can, and watch out for weird penmanship issues like that negative 1 there. I could have made a mistake if it didn't look like a negative 1 on the next run through. But finally, in this format, the t here and the t here cancels. That means direct substitution for t going to 0 will work. We'll plug a 0 into those two locations. So now this is equal to 2 divided by a root 1 plus 0 plus a root 1 minus 0. That's with the direct substitution, so we don't need a limit statement at that stage. And also, these both are just square root 1s, which turn into 1. So this is 2 divided by 1 plus 1. So it's 2 over 2. And that means this whole limit turns into a 1 altogether. Kind of a nastier one for sure. So this one was a challenge question, I'd say. Any questions, folks, on surviving that one? Okay, let's give this next one a try, and then we'll go over to problem 7. And well, this one looks worse at first, but I think it might be a little bit easier. Let's see if that's true. Sometimes you don't really get a feel for how hard it is until you actually just do the problem, so we will find out. So this one's another complex fraction. We have a denominator of x plus h squared here, another denominator of x squared here. So that would mean our least common denominator in this problem is x plus h squared multiplying just x squared. All we really did is take both the denominators that appear in the numerator and put them together for the least common denominator. Now, on this next step, we're taking the limit as h goes to 0. Let's write this out a little bit bigger. The punchline to this least common denominator is that we're going to multiply it into all the numerators. It'll multiply here, here, as well as here. We think of h being a numerator, since that could have been thought of as a h over 1. It's just not necessary to write it in that way. So we'll have x plus h squared here multiplied by, or excuse me, which is under x plus h squared times x squared, then minus x squared down here multiplying the same quantity, x plus h squared, times x squared. Lastly, h has to also be multiplied by x plus h squared times x squared. So if we multiply every single term in the numerator and the denominator by that quantity, x plus h squared times x squared, we're not changing anything algebraically. This equality right here is still true. But the benefit is now we can cancel x plus h squared. On the next term, we can cancel those x squareds. And, well, we still have a mess, but it's improving as we go. Its limit, h goes to 0 of x squared minus x plus h squared over h times x plus h squared times x squared. Now, there's still a lot of good algebra review to do on this problem. And as it stands right here by the red dot, at that step, this would be a pretty routine looking exam kind of question to get through. The next thing we have to do is navigate through this portion right here. For this problem, I would say where it's highlighted in green, that's kind of the trickiest part of the entire thing. So let's work it out on the margin. Negative x plus h squared really means take negative of x plus h times x plus h. What I would do to expand this is first do the foiling of x plus h times x plus h, distribute the negative last. So we'll go negative by the red dot. Well, if I can get it to hold still, there we go. Take x, distribute it into the group x plus h. You'll get x squared plus xh. Do the same with the h over here. You'll get hx, which is just the same as xh if you prefer to write it that way, plus h squared. That means it's negative of x squared plus 2xh plus h squared, which means after you distribute the negative, it's altogether negative x squared minus 2xh minus h squared. So that plugs into this location, highlighted in green. And this turns into the limit as h goes to 0 of, now we're ready to write in our total answer. So x squared first, everything highlighted in green, including the negative sign, turn into that. So it's minus x squared minus 2xh minus h squared, all of which is divided by h times x plus h squared times x squared. Lots of algebra on this one, but good review on getting through those things. Once we're here, we see a cancellation. Positive x squared cancels with negative x squared. Our goal is to eliminate that h right there by the red dot. To do that, I'm just going to factor out h from here to here on the next step. But any questions so far, folks, to this stage? Okay, so here's our next step. Limit as h goes to 0 of, I'm going to factor out h, so it's going to be h times negative 2x minus h. Then again, we have h, x plus h squared times x squared down below. So here's our last cancellation that we needed. With that gone, we can now take the limit as h goes to 0. That term there will go to 0, as will that term through direct substitution. So we're about ready to write our answer. It's going to be, after writing down negative 2x minus 0, then down below it's going to be x plus 0 squared times x squared. Then we just have to simplify this one. In the numerator, it's just a negative 2x. In the denominator, this is really just x squared. So it turns into x squared times x squared, giving us x to the power 4. So last step, one more cancellation. X divides into x, and we get negative 2 over x cubed. So this one is a different limit than we've seen altogether, because notice x is still in the problem. What we really calculated, we'll say later, is this is a derivative altogether. It turns out the limits that we're calculating right now are pretty similar to the ones we're going to see in chapter 3 once we define what we mean by derivatives. Well, any last questions, folks, on this one before we take a look at 7? Yep, you bet, Diana. Thanks for asking about that one. Okay, let's take a look at that problem 7 next. Oh, that's a really good one. Sketch the graph of a function satisfying all these given properties. And this is a good help on the upcoming quiz number 2 as well, I'd say, since that's what quiz number 2 is all about. Let me just get to a new spot here. Okay, looks like this will be our last question for the day. I don't have any special math department meeting like I did last week on Wednesday, so I'll be able to have ordinary office hours from 3:30 to 4:30 if you have additional questions today. But let's make this our last one. It looks like I might go past the 3:15, so just a reminder, you're not required to stay here. But I like to make this the last question of the day since, I mean, it is a great review question, and you can always come back to see it on the video. Okay, so it says, sketch the graph of a function satisfying all the information. Our sketch has to pass the vertical line test. I'd probably usually just start it off like this. Usually the x-axis I make a little bit bigger. Then let's take a look at what all this information is saying. We have limits when x is going to 0. But that negative sign means that we're approaching from the left. So we have to reach a height of 2. I'll put an open circle here. Let the curve come in, and that's this limit right here. It says when you come into 0 from the right-hand side, the height of the curve is 0. So let's put in another open circle here. Coming in from the right-hand side means the curve is generating this way. It gets lower and lower till it gets closer and closer to the height of 0. We made both of these open dots. Let me just do that to remind me which ones are done. Actually, that's kind of hard to read if you're looking at them. Check marks make sense. There we go. I used open dots on both of these because right here when it says f of 0 is 2, it gives us a choice and it means the top one had to be filled in. So that fills in 3 different parts. Any questions to this stage of the curve? Okay, looks like a couple more to go. Something happens around the number 4. We have a limit from the left, a limit from the right, and a function value. So let's do as we did before. Let's go over 1, 2, 3, 4. Now, if we come in from the left, that's 4 with a negative sign as a superscript, the height has to be around a height 3. So let me put an open circle here. And now we can connect our curve, let it come in. Also, the curve on the left, I'll just let it generate that way, point an arrow. Last one over here, it says as x approaches 4 from the right with that plus sign, the curve has to be closer and closer to a height of 0. So just like on the last portions, I'll put an open circle here at 4. Let the curve come in this way. And the only last thing to do here is f at 4 has to be a height of 1. That's just going to be another solid dot at that height. So that's how these kinds of questions would go. When it says your function must pass a vertical line test, what it means is if we have something that goes like this, that's a failure of the vertical line test in this way. A vertical line has hit the curve twice. So look through your problem, make sure none of that ever happens, and then you'll be in great shape. Well, any last questions with this one, folks? Okay, well, I need to take a short break, but if you do have additional questions, I'll be back in Zoom at 3:30. Have a great night, folks. Oh, night. Well, I guess a great afternoon. It's only 3 o'clock. Yep, thanks, Kaylee.